now I'm going to talk about the radial wave functions, okay? So, although we have used the convergence of the radial wave functions to derive the energy eigenvalue, the quantization of the energy, we really haven't worked them out in detail. Okay, so, but the first few, by using the recursion relationship, you can work out first of the few, which I encourage you to do. But I will also set a problem in the third assignment on the general properties of these radial wave functions, which are known as the polynomial part of it is known as the Laguerre polynomials. Okay. So the full wave function, of course, is going to have this radial part and the part which is the angular part. Okay. So, and if you work out what the radial wave functions are, they look like this. So here we see 2r, or 2r minus r. So here we see a polynomial part. Okay, so this is the polynomial part. And the rest is the part that we know we are going to have because of the convergence. Okay. We know that e to the power minus kr is something we are going to have, right? So this comes. So so now we can look at these profile and look at the probability of finding the particle, say somewhere near the vicinity of the nucleus. So if you plot those, then these are the functions that we get. Okay. So let me make this a bit smaller. So the first plot, the first one, is what it's saying is that it's 1 S. S is, as you know, is angular momentum. L equals to 0 is called S. Here you see U squared n 0. So the angular momentum value is L is 0. And they basically, as you know, I told you that for S equals to 0, the particle can get pretty damn near the nucleus, right? And if you look at here, you see the lowest energy state, of course, is going to have its maxima right where we expect the hydrogen, the Bohr radius to be, right? So this is Bohr radius, okay? And here, this distance is measured in Bohr radius. So this is exactly 1, where this thing is having its maximum. But if you look at the second excited state, you see that it's also non-zero near the damn near the nucleus. And similarly for the third excited state, fourth excited state, the S means that all of their angular momentum L is 0. And now if I look at all these states, of course, the first excited, the ground state is only going to have S. It's not going to have a P value for its angular momentum, but the second excited state will. And here we see that they're much farther away from the center, okay? And similarly for the fourth. So here this is going to be the average. But it's interesting to see that, the third excited state, the electron, it can sometimes come very near the atom, right? Near the nucleus. It doesn't always have to be further away from the second particle, second energy state. It can sometimes go even closer, as close as the second excited particle, This is very, very interesting. And okay, and then similarly the fourth. Okay, any questions about this?
So why does it go closer? Like, when does it happen?
When S is when angular momentum is 0, right? Remember that our if I look at the if I look at the equation for the the radial equation, there's an angle that here you see there's an angular momentum barrier,
Yeah,
and
yeah.
this barrier is not there when L is 0, right?
Yeah.
So that's why for L0, the particles can get very near the nucleus. In fact, the electron can be found in the nucleus, not something we expect topically, right?
Okay, that's a first.
No, that's quantum
Okay.
mechanics. That's see that if I expand this, I mean this is 0, of course, exactly at the nucleus, but very near the nucleus, it's not 0. So
Yeah.
there is a non-zero probability that you can get the electron very close to the nucleus, right?
Yeah, I see. Yeah.
Okay, but only for the zero angular momentum. For the higher angular momentum, see that it rapidly goes to 0 before it reaches the nucleus, right? For the higher angular momentum values. Also, for higher energy, it also is smaller, right? So now, this is the radial behavior. We can multiply with it the angular part, as these are things you derived before, or I told you to derive, and then you can combine them. And if you combine it, you see that wherever L is, wherever we have L0, like this is L0 is constant. So so 1s is just a sphere, 2s is also two spheres. So the two colors mean that they're two different maxima. So if I go back, you see the first one has one maximum, but the second one, 2s, has two maximum, right? Here is one maximum, smaller maximum, and here is the bigger maximum, right? And that is basically this picture. This is the smaller maximum, and the blue one is the bigger maximum. And then if I go to L equals to 1, then SP, right? Then basically we have, whether you are looking at something that is oriented in the Z direction or not, these are the different kinds of, wave functions you get. So these are the taking into account the three-dimensional nature. And if you take cross-section of this, then this is what you get. And whenever you have L equals to 0, you see that it has spherical symmetry here, 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 okay? But when you don't have L equals to 0, then, we'll have interesting pattern in terms of theta. Okay, so this is basically what the probability density looks like around the hydrogen atom. Okay, any questions? I highly encourage you to play with this. Like, fire up your Mathematica, take these, do plots, get your hands dirty, okay? I mean, this is beautiful. This is chemistry, in action. Well, this is not yet chemistry, but, this is the foundation of chemistry. Chemistry never made sense to me until I studied quantum mechanics. I was very bad at chemistry all my life until I had studied quantum mechanics. So, nothing to be proud of, but that's just what happened to me. Okay, any more questions?
No, sir.
So I might just spend half of next lecture just talking about the spin, how spin sort of affects the hydrogen atom, and then move on to path integrals. Okay, so don't miss next lecture.